Dear students, today's topic is Compton scattering and Compton effect. This Compton effect was discovered by A.H. Compton in 1923. This is the phenomena of scattering between a photon and a charged particle, usually electron. In the experiment, Compton observed that when monochromatic X-rays are made to incident on a metal having low atomic number like carbon, the X-rays were found to be scattered with longer wavelength. He observed the change in wavelength after scattering. In addition to the incident wavelength, a longer wavelength was also found during this scattering process. The incident photon loses its energy during the collision and hence it scatters with longer wavelength or lesser frequency. Lesser energy, lesser frequency or longer wavelength. This elastic interaction between the photon and the electron, the charged particle, electron, is called as Compton effect. In this Compton effect, both energy and momentum are conserved. Elastic means both energy and linear momentum are conserved. Using these facts, now let us derive the expression for Compton shift. That is, the difference in the or change in the wavelength before and after collision. Change in wavelength, also called as Compton shift. Let us derive the expression for that. Here, the incident photon in energy is E1 is h nu 1. Incident on the electron, so this is the electron here, electron initially at rest. After interaction, after collision, the gamma ray gets scattered along this direction, making an theta with the incident direction, and the electron gains energy, kinetic energy, recoils in this direction with an angle phi. So during the process, X-ray gets scattered and electron gets recoiled. Let us apply the conservation of momentum. Let P1 and P2 vector be the linear momentum of the incident photon before and after collision. P1 that of the incident photon, P2 the scattered photon. And let P suffix C be the momentum, linear momentum of the recoil electron. By applying conservation of linear momentum, we write momentum before collision equal to momentum after collision. And from this, we get PE vector is equal to P1 vector minus P2 vector. Now, the dot product of this expression by itself is taken. Taking the dot product by itself, PE vector dot PE vector is right hand side, P1 minus P2 dot P1 minus P2. We know that dot product of two vectors is the product of the magnitudes and cosine of the angle between the two. So that we get PE square here and right hand side P1 square plus P2 square minus 2 P1 vector dot P2 vector. And again this 2 into P1 vector dot P2 vector is 2 P1 P2 cos theta. This is PE vector. But energy and momentum are connected to each other by this relation. E is equal to PC or P is equal to E by C. This we get from the expression E equal to MC square or E by C is MC, hence P is equal to E by C. Substituting that here, we get this expression. Taking P1 as E1 by C, P2 as E2 by C, we get this, or by simplifying 1 by C square common, we get this expression. Let the expression be 1, equation number 1. Now let us apply conservation of energy. Here energy is conserved. Energy before collision equal to energy after collision. So here energy before collision, that of the incident photon, E1 is its kinetic energy h nu 1 and m0 c square is the rest mass energy of the photon, that's equal to energy of the scattered photon and the kinetic energy of the recoil electron. This is the relativistic kinetic energy. So that we get this equation. Now simplify. E2, we take E2 this side, left to the left hand side, we get this expression. Squaring both sides, we get this. And now from this, PE square C square is E1 by this. Or from this, we get PE square as 1 by C square into E1 minus E2 plus m0 C square minus m0 square C square. Here 1 C square gets cancelled with this C square, this C square. So that P square is given by this. And here again, further, E1 minus E2 whole square is simplified as E1 square plus E2 square minus 2 E1 E2, so that we get this expression. From that, we get 1 by c square into this. See here, these two terms, they cancel each other. Here, this minus m naught c square is taken inside the bracket. 1 by c square common here. So when you take this one inside, this c square becomes c power 4. So that these two terms, they get cancelled, we get this. Now, equations 1 and 2, both are the expressions for momentum square of the electron. So that by equating them from 1 and 2, by equating them, equate 1 by c square gets cancelled, and when we simplify, we get E1 minus V2 as E1 E2 by m naught c square into 1 minus cos theta. See here, E1 square into square, they get cancelled. Then 2 E1 E2 cos theta becomes 2 E1 E2 minus this, and this term becomes, take this term the left hand side, becomes minus, it's also minus. However, you simplify that. You simplify, we get this. In the next step, we write the expression for E. We have energy E equal to h nu. And nu is nothing but c by lambda. We have velocity c equal to nu into lambda, so that nu is c by lambda. So substituting E as hc by lambda. E1 is hc by lambda 1, hc by lambda 2 equal to this much. Lambda 1, lambda 2 are the wavelengths of the incident photon and the scattered photon. There, say further simplification. Here hc common, 1 hc gets cancelled here. Remaining 1 by lambda 1 minus 1 by lambda 2 equal to this. Or further simplification is so left hand side is 1 by lambda 1 minus 1 by lambda 2 is equal to, in the right hand side we have h by m naught c lambda 1 lambda 2 into 1 minus cos theta. And simplify the left hand side. Lambda 1 lambda 2 common denominator, numerator lambda 2 minus lambda 1 is equal to 1 by m naught c lambda 1 lambda 2 1 minus cos theta. So that lambda 1 lambda 2 gets cancelled. Lambda 2 minus lambda 1, change in the wavelength of the scattered photon and the incident photon, let it be d lambda. So that d lambda is, this is h by m naught c into 1 minus cos theta. So d lambda is h by m naught c into 1 minus cos theta, and this is the expression for Compton shift, change in wavelength or Compton shift. Suppose theta is equal to 0. Theta 0 means the X-ray photon, the photon gets scattered in the direction of incidence. Theta 0. In that case, cos 0 is 1, so 1 minus 1 0, d lambda becomes equal to 0. D lambda is equal to 0, no Compton scattering in the direction of incidence. No change in wavelength, no scattering in the direction of incidence. Suppose theta is equal to 90 degree. In that case, d lambda becomes cos 90 0, it is h by m naught c, and this wavelength is called as the Compton wavelength. D lambda is the Compton shift, the exact value h by m naught c is called Compton wavelength, and this is the theory of Compton scattering. With this I stop here. Let us continue the next class with some other topic. Thank you.